societally relevant science means changes depending upon who you talk to. And there was supposed to be a movie here from one of our high-res simulations, 10th of a degree ocean and sea ice model, and the colors were showing the sea surface temperatures, and the white areas were showing the ice extent, but it doesn't seem to be working here in any case. So, okay. As many of you know in the audience, how many of you are familiar with the global Earth system models? Probably many of you use it already, right? Okay, not bad. So they are simply models. They use physical equations to simulate key fields and processes in the atmosphere, ocean, land, sea ice, land ice, and all the remaining components, including the ocean biogeochemistry. Because of the computational constraints, resource issues, when they are discretized, as shown on the right side here, simply because of discretization and simply because of the processes that remain, many of the processes remain below the grid scale, then they need to be parameterized. I'm not sure how many of you are familiar with the parameterizations. Parameterizations are trying to represent physics that are not represented explicitly by the grid, and they are trying to mimic the impacts of unresolved physics based on high-resolution process models or based on observations. And all of the parameterizations, yeah, I don't think that I'm incorrect to say, I'll just say change it to most of the parameterizations, use resolved model variables to represent the impacts of unresolved physics or unresolved chemistry. And those, that's what we call parameterizations, and they require a lot of work. Some of them have been in development over 10 years. For example, vertical mixing schemes within the ocean model, they represent microphysics, and you cannot clearly represent order millimeter time, spatial scales. So all of those things need to be parameterized with the resolved model physics. And these representations are, as I said, building on process models. They are high resolution models trying to represent those physics or observations or so-called large eddy simulations. And you can see on the lower panel here, there are so many processes an Earth system model needs to represent, and they are all, I mean, they are shown here, winds and waves, for example. We have a wave model. It represents actually explicitly impacts of waves. But if you look at in the ocean interior, vertical overturning, that's usually vertical mixing processes are not explicitly represented and they need to be parameterized. And just to make sure that Peter is happy, we have land processes in the whole system as well. By the way, I forgot to mention that I'm an ocean modeler. And as Betty indicated, my background is quite different also. My undergraduate is in mechanical engineering. My graduate degree, PhD, is in aerospace engineering. But the common thing between all of those is fluid mechanics and fluid dynamics. In engineering, you don't have F. As soon as you deal with whatever the larger scale phenomena, then you have to include, of course, the Coriolis force. So that's one of the main differences. Okay, so global Earth system models bring all of the components, such as land, sea ice, the atmosphere, ocean. We have the runoff also, and all of those components together. And CESM, Community Earth System Model, and Betty already gave sort of its history, brings in all of those systems together. And the schematic is shown here. We have at the center a coupler, which is used to exchange states and fluxes needed to drive each component model. We have the atmosphere model, we did this chemistry and a high top version that goes all the way to stratosphere all the way. And we have the sea ice model, we have the land ice model, representing glaciers, for example. We have the ocean model. And since I'm an oceanographer, that's the most important component of the climate system. We have the marine biogeochemistry modeled within the ocean model. We have the land model, and it's including its land biogeochemistry, river runoff, and surface waves is included. They're included in the model as well. So, and then for example, in historical simulations, the forcings are embedded in or provided to the atmospheric model. They can include greenhouse gases, anthropogenic aerosols, volcanic eruptions, and solar variability. So one thing to keep in mind in global Earth system modeling, or I think these are also true for regional modeling system as well, there is generally a tension or competition between three things: model complexity, and it's shown in the center plot here, model complexity, model resolution, and ensemble size. And depending upon what your research question is, and perhaps more importantly, how much resources you have will determine what complexity, what resolution, and what ensemble size you would like to use in your research. So on the upper left plot here is showing the growing complexity of Earth system models. When the sort of couple modeling started, there were only two components, atmosphere and the ocean. And for a while, for roughly 2 decades, nothing got added. But starting in late 1970s, additional component models were included or started to get included in the whole system. And you can see that as we approach to the present, that the thickness of that line grows considerably with additional components. Another thing shown on the upper right here is that as we include model components or missing components, previously missing components, the models themselves are getting also complicated. We keep adding more features. We keep adding representation of missing physics continuously. And that's represented in the schematic by the thickness or the height of those cylindrical shapes. So they are also getting complicated. And then as we increase the computational power, just human nature, I guess, we tend to go to higher and higher resolutions. When I started working on climate models about 30 years ago, I called it the real ocean, which was 4-degree by 3-degree ocean model with 20 vertical levels. And it was sort of the state of the art at that time. And you can imagine that that's now not even the standard for garbage science or whatever, I don't know. So the resolution, there's the desire to increase resolution as the computer resources become more and more available. Finally, in the past, again, 20, 30 years ago, because of the lack of resources and all that stuff, we were quite happy if we have one simulation of the historical period, because that's all we could afford. And the ensembles or anything like that were just big dreams. But now with the additional resources and also with the realization that I mean, it's like if you just change make changes at the round-off level, then you get substantial differences a few weeks later in the climate system. So people are now recognizing the importance of ensembles, and that's shown here. You start from an initial state seemingly very similar, but then as you integrate in time, it's just like the butterfly effect, right? It just, the paths of the system changes quite a bit, and then you get a huge ensemble spread in your fields. So depending upon your science question, depending upon your research question, one of the first things that you are going to tackle in your research, balance of these three seemingly competitive things. You need to decide on the complexity of the model. whether your model setup is adequate to address your science. Similarly, what resolution should you use, and how many ensemble members do you need? And how many ensemble members you need strongly depends upon the question that you are asking. For some fields, maybe 10 members are enough, but for some other questions, maybe 50 members will not be enough. So that's an important thing to decide. And of course, you have to, the big factor here is how much resource, your time and the computer time you have. So going back to CESM, I have no idea why this is showing up like that, but anyway, Betty already indicated CESM is, we have been we've been actually involved with climate modeling over the last 30 years. It started in mid-1990s or early 1990s, and I was lucky to be here at NCAR at that time when the whole thing started. And today we have 12 working groups. Most of them are actual model development working groups, such as the atmospheric model working group and the ocean model working group or land model working group. But we have a few application working groups as well, such as Earth System Prediction Working Group and Climate Variability and Change Working Group. The point of this slide is that CESM, as the C implies, is a community-based model, and its governance reflects that. All of the working groups have at least one non-NCAR co-chair. We have a CESM steering committee. Of the 12 members, 10 of them are external. The only internal members to NCAR, myself as the chair of the CESSC, and our lab director, Jean-Francois Lamarck. And we do have an advisory board which consists of completely external members to NCAR. So that's important to stress, I think, the community aspects. So we also have a community approach to software development. CESM, we have stopped releasing CESM, I think in summer of 2019. That was our last release. There is no such need anymore because all of the code is available as open source community model via GitHub. So if you want to see our latest model, not necessarily greatest, but latest model version, you can access that via GitHub. And this has been a game changer for us in terms of community being able to access and contribute to the latest development code bases. All of it is very transparent. If there is an issue, you can see it right away there. Likely there are notes associated with that particular thing. And development priorities and bug tracking are completely available for the community to access. This is actually quite different than controlled access, because it was requiring somebody to control the access, make sure that people are aware of what the issues are. But with switch to GitHub, those are all gone. The downside of this thing is our sponsors, such as NSF, would like to know how many people are actually using CESM. And when the funding time comes, that's one of the first questions to get asked. But with open access policies, with the code base and with the data, and then with the privacy concerns, it's extremely difficult for us now to be able to pinpoint how many people actually are downloading CESM or downloading CESM data sets for their research purposes. So one of the success stories with CESM is that it supports a quite wide range of climate science goals through a single model code base. You'll likely see examples of the CESM code version on the cloud here, I believe, in this tutorial. But CESM can be used on a desktop, for example, as a single column model, and that can be used for parameterization development purposes. It can be used on small clusters. This can be quite beneficial for university users to run the model on their sort of local system. And this can be run on coarse resolution, and it can be run, for example, for paleo applications that require long simulations. And finally, on the other side, extreme side, it can be used on high performance computers to perform what I call medium and high resolution or ultra high resolution simulations. They can be used for coupled model intercomparison project purposes that contribute to IPCC that was mentioned earlier. It can be used for large ensembles, or it can be used sort of frontier science questions, for example. Keeping up with the tune of team of sporting a range of science applications or goals, in CESM, all component models can be run in active mode. So they're all fully active. All component models on the opposite end can be replaced with their data versions. So that means if you want to, for example, run the ocean model by itself, you can do so simply by providing atmospheric data sets needed to run the ocean model to determine the surface fluxes. We have many idealized model options within the system. Most of them are on the atmospheric side at this point, such as single column atmospheric model. I don't like the acronym. It's a SCAM model. I don't know why that name SCAM, but anyway, that's what it is. It can be used with different moisture properties. We have a slab ocean model. Although when you're an oceanographer, slab ocean is a four-letter word in the ocean modeling community because we don't want an ocean model to be just like a slab model. We have numerous choices available within each component model in terms of their parameters and parameter settings. And every day, as I indicated on that complexity table, we keep adding more and more physics that were previously missing in the coupled system. So that increases the complexity. But again, you can run it in simpler model configurations if it is what is required for your research. So in terms of community engagement, CESM, I think, is one of the, I think it's the only model in the climate modeling community. It is truly a community model. And we have annual workshops. They happen, well, in June usually. And then we have each working group also their winter working group meetings. In person, when we have the annual workshop in person, we had 300 to 400 people attend that, and this room was one of the venues, and we had literally 300 to 400 people sitting in this room without the desks. When we switched to the virtual environment during the past 3 years, our attendance went up to 700 to 800 people, but it is difficult to judge how engaged that group is. Usually people, as you know, with the virtual environment, you do 10 things at the same time, and your attention is really not much for one particular thing. So the productivity and creativity go down quite significantly. So that's why I think it's important to have in-person meetings like this. Okay, and then another point of being a community model, we have tutorials, and this is the CESM annual tutorial. We do also have shorter versions of this tutorial at AMS and AGU meetings. They run either half a day or 1 day, and they are sort of compressed versions of these. So if your friends, or if you are still interested in learning more about CSM, you may want to take a look at those tutorials. And you are probably already aware of our web presence. Many of the tutorial materials are already on the web. And as a community model, we need to be also cognizant of community needs. Community has a lot of questions, and we have forums. They are answered. And this is just an example of this. This is showing what kind of questions can be asked or are being asked, and they are being answered. And the community members can answer these questions as well. And then we have also lots of documentation in terms of model use, how to name your experiments, how to name your data sets. And I just also recently updated the CSM data policy, and you may want to also take a look at take a look at what it says in terms of what we can store and what needs to be stored, perhaps, with respect to model output. Okay, so this was sort of a brief introduction to our capabilities and our community sort of engagement efforts. Do you have any questions so far? Okay, so if not, I will try to now, in the second half of the presentation, try to show you some of our recent efforts. I'll try to show you some highlights and also try to answer some of the questions with respect to equilibrium climate sensitivity, which is an important topic, I think. So, as we mentioned before, one of the activities or one of the efforts that we do is to participate in a coupled model intercomparison project. And the results from that project or those simulations, are you familiar with the coupled model intercomparison project? That's the latest effort, the CMIP6, and it is asking for coordinated simulations from interested modeling centers. There is a deck set of experiments. They are mandatory usually, and there are multiple order 20 to 30 or even 40 MIPS, model intercomparison projects, sort of they are satellite MIPS around the deck simulations. So that was one of our major activities over the last 5 years or so, and we have arranged for an EGU CSM2 virtual special issue. And if you're interested in learning more about these simulations and their analysis, you can go to that publications website, or you can just go to also AGU website to access all 50 manuscripts. They are published, and they are all free access, so you should be able to access them without any issues. I just included the primary manuscript here that was published in 2020. And then early last year, Jean-Francois and I wrote an article or opinion piece in EOS to introduce the special issue as well. And I think that's, if you're interested in, that's a short article that you can just quickly learn about challenges that we encountered during this development process. So one of the successes of CESM is that it is collaborations with the community, not just within the United States, but also external community. And we get quite a few requests for collaborations. And I believe that the reason for such requests is the model fidelity of CESM, its simulations. And I'm showing an example here from John Fosulo. It's published in GMD. He has developed a toolkit called Climate Model Analysis Tool. And this is showing a summary of model performances across roughly 35 or 36 models that participated in CMIP6, considering energy, water cycle, and model dynamics. And those are color-coded. The fields related to energy are in, for example, orange. Fields related to water cycle are in blue, and the dynamics-related fields are in purple. And then compared to observations and compared to reanalysis products, a score is given, and it's considering the mean, annual cycle, and some short-term variability. So, and then there's an overall cycle, overall score at top as well. In this plot, if you are on the red side, it's good. If you're on the blue side, it is bad. So you can see that I underlined, we contributed with 4 model configurations to CMIP6, and I underlined the ones that are associated with CSM here. So I was quite happy to see that of our, we are in the top 10 with all of our 4 configurations. So I mean, some people don't like model intercomparison projects because it becomes sort of some kind of context. My model is better than yours, but it has it has some benefits. It can expose model errors and all that stuff. But in this case, I would like to stress that when we get collaboration requests from external folks and all that stuff, this is one plot they tend to look at to recognize the fidelity of CESM and it is solutions. So that's, I think, an important aspect to stress. How many of you are familiar with equilibrium climate sensitivity? Okay, there are some people familiar, maybe quarter or 1/3 of the audience. So for those of you who are not familiar with equilibrium climate sensitivity is, it is in a sense hypothetical thing. It gives you how sensitive your coupled model is to a doubling of CO2 concentration, instantaneous doubling of CO2 concentration, and how high the surface temperatures go up. So it's a measure of sensitivity of the surface temperature to increase in CO2 doubling. But when I say hypothetical, equilibrium is in the word, in the phrase, equilibrium climate sensitivity. Clearly, in order to get to equilibrium, you need thousands of years because of the diffusive time scales within the ocean model. In this case, it represents an estimate of equilibrium climate sensitivity. And if you are familiar with Gregory et al. Methods, it's essentially an extrapolation of a regression line, and it's usually referred to as effective climate sensitivity. But in any case, CESM was one of the models, or is one of the models with a large equilibrium climate sensitivity above 5 degrees Celsius. We don't know what it is, but the accepted range is usually around 3.5 to 4.5 degrees Celsius or so. And it is, I mean, it has some, these estimates are based on some paleoclimate approximations or records as well. But in most cases, it is, people think that it shouldn't be less than 3.5 perhaps. And if it is more than 4.5, maybe it's not the right value. So it is sort of an expected range, I would say. It's not, that's what people want to see their equilibrium climate number to be. So our climate working group spent quite a bit of time trying to figure out how the present model setup would behave under last glacial maximum simulations. What is shown here is a scatter plot of the last glacial maximum global cooling for surface temperature plotted against equilibrium climate sensitivity. You can, and then the shaded regions are estimates. The vertical one is estimate from the paleo records for the surface cooling, and the horizontal lines are the ranges for equilibrium climate sensitivity from IPCC reports. The previous model values were along the CSM model versions are shown by the black dots here. So they were within these estimated ranges, but you can see the CSM2, which is the red dot there, it is outside these. The point here is that maybe equilibrium climate sensitivity is not that important, but when you run a last glacial maximum, and if your surface temperatures are minus 12 degrees, as opposed to be less between -5 and -7 degrees Celsius, then that's a problem. So they went back and checked, spent roughly 2 years, and looked at cloud feedbacks, aerosol cloud feedbacks. And they found that a particular parameter setting in the microphysics scheme in the atmospheric model related to mixed phase clouds, it was limiting the number of ice particles in that scheme. And once they took that limit away, and it was, my understanding is it was there inadvertently. Once they took that limit away, they obtained the blue dotted line. So you can see that both the last glacial maximum surface cooling and equilibrium climate sensitivity went down quite significantly. So now this version of the model is within accepted ranges. Of course, last glacial maximum is okay, but then you have to also look at how it's behaving in present day or historical simulations. So the new what is shown here is the temperature anomaly with respect to the, I think this is for the 1850 to 1900 period of the surface time series, surface temperature time series, anomaly time series. The observational time series are shown by the black lines. Other lines are showing estimates, other lines are showing the previous model versions, including CSM1 large ensemble spread. And then you can see that the new simulation, paleo-calibrated one, which is given by the blue line here, is actually duplicating or replicating rather observed historical surface temperature trend quite nicely. Another effort that we have, and it may be of use to quite many of you, is the CSM2 large ensemble. And this has been completed. This was a partnership with the Institute for Basic Science, Center for Climate Physics in Busan, South Korea. They provided the computational resources. We have completed a 100-member ensemble for the 1850 to 2100 year period, using the SSP 370 scenario for the future extension. These use a combination of macro and micro initializations. Micro is just simple atmospheric perturbation at restart. And then macro is using different states for all component models, particularly the ocean component. We have 50 ensemble members with CMIP emissions, CMIP6 emissions for biomass burning. We also conducted another 50 members using a smooth version of the biomass burning. All of these, again, are available at this website. And if you're interested in, the manuscript is given here. I suspect that this will be of use to quite many of you. A complementary set is the so-called single forcing large ensemble experiments. These use, again, the same setup as the CSM2 large ensemble. But in these experiments now, we are fixing certain forcings and allowing only one forcing set to change. We have done 4 ensembles of 15 members each for the 1850 to 2050 period. And these are the greenhouse gas only, anthropogenic aerosols only, biomass burning aerosols only, and everything else only experiments. So for example, if you take the greenhouse gases only experiment, in this case, the only forcing that's being changed is that forcing. All the other forcings are staying at 1850 levels. All the data sets we are hoping that will be available by the end of this month. Ayla Simpson is leading the manuscript. She's about to submit that. And as soon as it's submitted, we'll make all the data sets available. And the plot over here is showing the surface temperature anomaly time series with respect to 1920, 1940 period. You can see the lens to large ensemble is the black line here, with the shading is showing, I think, 1 standard deviation, or some measure of the ensemble spread. And all the other individual forcings are given by different colors here. And the dashed purple line is the sum of 4 only experiments. You can see that it's below the black line. So there is some nonlinearity in the system. You are not recovering the full impact as shown in the lens to time series. And this is primarily related to nonlinearities in the system, in particular the mean state differences. And that's articulated in the manuscript that Ayla is about to submit. Okay, this was an application of these large ensembles. This is from the land model working group. What is shown here is maximum snow water equivalent plotted against the total runoff from these simulations. The blue lines are from the historical period, and it is showing that during the 1940-1969, that's for that period, snow accumulation is essentially buffering the effects of stochastic precipitation events on runoff. So in this case, there's a clear linear relationship between snow water equivalent and total runoff. But if you go to the future, and those distributions or regressions are shown by the orange lines here, the situation changes with because of the warming. The snow is melting, and that buffer is lost. That means the relationship between precipitation and snow water equivalent, or the runoff, for example, is becoming less predictable. It is essentially reducing the predictability of runoff and drought in the future, primarily reflecting the stochastic nature of precipitation fields. Oh, about 10 minutes at most, right? Okay. So another effort that we had, I'm using head here, was the CESM high resolution simulations. These are using 1/10 of a degree, nominal 1/10 of a degree ocean and sea ice resolution, and 1/4 degree atmospheric resolution. And we have completed a 650-year PI control, 80-year 1% CO2 experiment, 3 members of 1850-2100 transient simulation. We have completed all of the high-res MIP, that's one of the CMIP6 sort of satellite MIPs, coupled and AMIP type simulations. For those of you who are not familiar with AMIP is, it's the atmospheric model intercomparison project, and it is atmosphere only simulations. And we have also done 5 cycles of ocean only experiments, that's OMIP, for the 1958-2018 period. And we have also, in the process, we have completed an initial set of decadal predictions with this high resolution system. It was a collaboration between Texas A&M, us, and the Qingdao National Lab for Marine Science and Technology. And it got terminated in December of last year. But all of these simulations are available. Most of these are available to you if you're interested in looking into high-res simulations. Okay, I just wanted to mention that coming back to the actionable science part that I mentioned, this is showing examples from our polar climate working group. They are looking into, for example, in the Antarctic, interactions between polynyas and ocean biochemistry. And just to show an example here, the lower left panel, they are providing sort of information for decision makers where the future marine protected areas should be designated. We have some existing ones already, and they are shown by the bluish colors here. But the whitish regions, numbered from 1 to 9, are under consideration. So our polar climate working group, using CESM simulations, are trying to provide information as to which one of these regions should be given priority in terms of being declared as marine protected areas. Of course, this requires agreement between, I think, 26 nations, and 2 of the nations are Russia and Ukraine. So this is going to be a major problem, I think, going forward. Okay. I mentioned predictions, and I try to distinguish it from projections. So we are using CESM for subseasonal prediction purposes. And this example is using CESM with the high top atmospheric component. That's the whole atmosphere community climate model version 6. What is shown here is surface temperature forecast for weeks 3 to 4 after January 5th, 2021, stratospheric southern warming event. I don't expect you to be familiar with this event, but stratospheric southern warming events, it's associated with the breakdown of the polar vortex, and they are thought to be impacting the surface temperature, particularly in the, northern high latitudes. CESM simulation is shown in the middle, and the verification is a reanalysis product. Meritude shown on the left side. So we are doing quite well. And in comparison with all the other models participating here, these are postage stamp plots. I don't expect you to look at all of them in detail. You can take my word here. CESM is the best performing model in representing this warming feature in the northern high latitudes. But more importantly, in this study led by Nick Davis, they showed that actually the common thinking is that the stratospheric southern warmings are impacting the surface temperatures at high latitudes after 3 to 4 weeks. This study actually shows that that may not necessarily be the case. When they did, the way they did it, they essentially changed their initial conditions. Some of them did not include stratospheric southern warming events, yet they were able to produce the surface temperature signatures. So I think that's an important finding. Another thing, I mentioned that we have the high resolution simulations for decadal prediction. And what I'm showing here is 1 to 5 year average, wintertime, Northern Hemisphere wintertime, sea level pressure skill maps. The top is for anomaly correlation coefficient, ACC. The bottom panels are mean squared skill scores. The point that I wanted to make here, the reds are good, the blues are bad. The left panels are from the high res. The middle panels are from the low res equivalent with similar ensemble member size, 10. And then the right side is low res with 40 ensemble members. The bottom line is that it looks like, these are very preliminary, we are getting better skill with fewer ensemble members at higher resolution. So it's improving the skill essentially, despite being more maybe chaotic is the wrong word here, but despite showing more variability, it's actually improving the atmosphere-ocean flux interactions. This was an example to show we have paleo ice sheet simulations that are also ongoing. And this particular example is showing the last glacial maximum North American ice sheet simulation. And we are now, even though this particular simulation is offline, CESM has the capability of now using interactive ice sheets and multiple ice sheets. We can do it now with Antarctica as well as with Greenland. And we have just recently expanded our ocean biogeochemistry model. We use the MARBLE framework for this purpose. We have now included a second zooplankton type, and that is particularly useful for fisheries models. We are using the feisty fish model offline at this point, but we are in the process of bringing that particular fish model online. That'll be a CESM component, but this is still ongoing work if you're interested in. Talking about simplified models, I talked about increasing model complexity. We have a project, it has been going on for the last 2.5 years or so. We are trying to provide easy to use, simple model or simpler model configurations of CESM. And I believe Ayla will be talking about this in more detail, I don't know which day, but one of these days. And we have actually created a graphical user interface for the user to easily set up a particular CESM configuration with just simple push of buttons. So we think that this is going to be quite useful. We are at the trial stage with some guinea pig users, collaborators, but I'm hoping that this will be available to the broader CESM community. Okay, we have versions of variable atmospheric model. This is with the spectral element dynamical core. These simulations or these configurations are created by our university collaborators. You can see our existing grids. We have a high resolution Arctic grid. One of the most popular grid is the CONUS grid. It's the one, the middle, in the bottom row, it's the middle panel. It's essentially increasing the resolution to 1/8 of a degree over the continental United States. Just final slides. We are working on creating a new version of the model. I labeled this slide as towards CESM3. We have preliminary coupled simulations that use developmental versions of the component models. These, as many of you may know, the older version of the model use the parallel ocean program version 2 for the ocean. That's POP2. We have switched to MOM6. That's a GFDL model, a modular ocean model version 6. So that's the new model. It uses CI6 and it uses the development versions of CAM6 we are also increasing the number of vertical levels in the atmosphere. This is with 58 vertical levels, but we are hoping that the workhorse model will use about 92 vertical levels in the atmospheric component. Needless to say, each time we develop a new model, it is both a big scientific and technical challenge. So it has been taking us quite a while, and it will be probably, we hope to get some preliminary results by summer of next year. With respect to sort of future work, we are collaborating with the LEAP Science and Technology Center, that is the Learning the Earth with Artificial Intelligence and Physics. This is going to bring many machine learning, artificial intelligence aspects into the CESM. So CESM is going to be the primary coupled system in this effort. This is led by University of Columbia, and it has many partners, university partners and private partners as well. So this is going, I'm looking forward to this particular effort to bring in machine learning aspects. We also have a few other projects such as N2 lines that's focusing on bringing machine learning into the ocean, the new ocean component MOM6. And finally, we are about to get started on this project, which will be still 5 months, I think. We are trying to do enabled cloud permitting coupled climate modeling. The target resolution would be 3 kilometers or so within the coupled system. And the idea is to incorporate a non-hydrostatic dynamical core with the spectral element dynamical core of CAM. This would enable us both, this would bring in both Fortran and C++ versions of the model. And in that case, we can take advantage of the GPU side of the Drecho, the new computer system that's supposed to be on the, well, that's supposed to be coming hopefully next year. So with that, I'll stop and hopefully take questions. I know that I'm almost too much time. Thank you. Do you have any questions?
Well, thanks. Oh,
yeah.
Yes.
Well, so yeah, I mean, that's a good question because many, I mean, there's some, there are some challenges, of course. So I didn't go over the objectives. Maybe I should just briefly mention that the objectives of this proposal, the first one is, I think, important, improve parametrizations. So they will be looking at both atmosphere and land also, and ocean. They will try to look at if there are aspects of elements to improve existing parametrizations. And by machine learning techniques, one idea could be to replace the existing parametrizations with their machine learning equivalents. This can be, I mean, through emulators and all that stuff. So they are, if that can be achieved, then they're supposed to be cheaper, first of all, to run. Then the second aspect is that those machine learning-based parametrizations are better suited to run on GPU-based systems. So that would be sort of the 2 advantages. But of course, you can't just trust these as black box models. So that's why, I mean, NCAR collaboration with this particular group is quite important because we will be jointly evaluating, making sure that they are physics-based and they are doing what they are supposed to do. And then we are going to also provide our expertise from the climate modeling side. And it's not an easy adventure. I mean, then also It can be used, for example, leverage physics to improve machine learning techniques as well. So it is a complicated effort. I don't know whether I answered your question fully or not.
We're going to go to the break.
Yeah, sure.
So Gokhan gave an amazing introduction to the complexity of this model, and it can be a little overwhelming. I'm a geographer, so that's my background. I do land use, land cover change, and I'll be presenting some later. But one of the things to understand is this is a community model. So you're not expected to have understanding of absolutely every component of this model. As we go through this tutorial, you will learn about things that are outside of your domain of expertise and your understanding. And that's fine, because what you will be able to see is this tool that you can answer really complex questions about the future and the past and our current climate and how to use them for your research. As Gokhan showed, it's not just a matter of running the model. We have a large amount of data that's already coming out of the models we've run. So your research may be running the model, setting up experiments. It may be processing other models that have already been run. So as you go through this week, don't feel like it's a competition. You don't have to be competing against everyone to show how much knowledge you have. What it's really about is learning. And it's learning how these tools can be useful in your research context. With that, I think we'll go to the break.
Yeah.
We're running a little behind schedule, so we've got a 15-minute break set up right now. So we'll come back at 9:30, and Peter Lauritsen will give you an introduction and an understanding of the dynamics within the atmosphere and the atmospheric model. We have coffee at the back, and yeah, so we'll see everyone back here at 9:30. And thank you, Gokhan. That
You're
was
welcome.
great.
Yeah, and if you have any questions, I'm here, and I'll be here, I think, back on Wednesday as well. If I'm not mistaken, there's a lunch.
That's right, for
Yeah.
the meter scientist. Yeah. So thank you, Ron.